Okay, we've been working with polynomial functions, finding the zeros, using all of our theorems. We have one more theorem here, and it's not really all that impressive. It's called the complex conjugate theorem. And the idea is this: if you find that you have a solution that's a complex number, well, it has a conjugate, it has a partner. So suppose a plus bi turns out to be a complex solution. Well, A minus BI also is. That's its conjugate. I think we've talked about that before. So the A and it's the only thing that changes is instead of a positive, you get a negative. Those are the conjugates. Everything else is the same and makes a conjugate. Now, the reason this is true is pretty obvious. If you were doing the quadratic equation, you get negative b plus or minus the square root of b squared minus 4ac over 2a. Well, if you get a complex number, it's because of what's happening underneath the root. And if you get one of them, this plus or minus here is guaranteeing that you're going to get 2. So if you got an I involved, a complex number, the plus or minus is always going to get you 2 of them. So they always come in pairs, and it's always the plus or minus. Okay, so here's a problem that could use this fact. What we want to do is we want to find a polynomial that has all they've told us is these 3 zeros, and one of them is complex. So we know that, let's start to build this thing here. So here are my 2 real zeros, or negative 3 and 2. So remember, we changed the sign when we put them in here to write them as factors. So I is my third. Well, because I have I and negative I, because of this theorem, I know they always come together as in pairs, so I have this one as well. So basically I know that I and then negative I must also be a zero, a complex zero. Now what's this that they're telling us here? That if I put negative 2 in, it tells me that the function equals 100. Well, what's the point of that? Well, we have this a sitting in the front here that could be a stretch. So we don't know. Like, this would be the basic function here with all of these different roots, but I don't know about any stretch on the front. So to find a, we're going to put negative 2 into the equation. And we know that when you put negative 2 in, you get 100 out. So they're expanding it, but actually I wouldn't do that. So I would have been fine with you leaving it just like this, but finding a. And finding a would actually be easier if we left it in this form here, which is actually what they're doing here as well. Like, I would not need you to multiply this out. Okay, so we're putting negative 2 in there, and when we put a negative 2, it's telling us we get 100 out. So they're doing all the math for us here. But if you crunch all this down, it all turns out to be, all of this turns into negative 20. So if that's negative 20, we divide both sides by negative 20. So my stretch factor must be negative 5. Okay, so let's play the same game here again. Now we've got a degree 3, so we know we have the fundamental theorem of algebra tells us there's 3 values. Now they've given us 2 of them, so let's go ahead and start building. I've got x minus 5, remember it's built with a negative, and I've got x plus 2i. It's built with a negative. Now there has to be, if negative 2i, because it's complex, 2i must also be a solution. So we can then go x minus 2i. All right, now there's a stretch factor in the front. So here's what we've got. F of x equals a with all that stuff there. Now let's put in 1. And when we do, we know we get 10 out. And we're trying to solve this stretch. So I'm putting in 1. Okay, now we've got some work to do here for us. Let's see. Now I'm going to go over here and I'm going to multiply these 2 guys together. So if you remember how complex conjugates work, so when you multiply these, the middle term is going to just disappear. So it turns out to just be the square of the front and the square of the back. Well, that's going to get 4i squared. Well, I squared is negative 1, so I've got 1 minus, well, let me do it like this. And that's going to be 1 minus 4. It's going to be negative 3. So these multiplied together create negative 3. Now we just keep going. I've got 10 equals a. That's 12. So a is going to be 10 over 12. or 5/6. Okay, now in their example, they went ahead and multiplied that all the way through. I don't have any problem with you just leaving it like this. It's a much more useful form with it factored like that. And so that would be my function. And I've got a degree of 3 because I've got the 3x's. Okay, next we've got Descartes' rule of signs. And I have never found this to be all that terribly helpful, but it's clever. So if we wanted to get some more information about our roots, our zeros, what we could do is we could find out how many of them are potentially positive and how many are negative. Now I'll talk you through one here and I'll show you what I mean. Again, I don't think it's all that valuable, but here it is. So Descartes figured out that if you could just count up the number of sign changes, you could get some useful information. So here's what I mean. Here's the function. Is he changes from negative to positive and positive to negative. There were 2 sign changes. And so he found out that the number of positive real roots are either 2 or 0. It always goes down by an even number. So we saw 2 sign changes. So he's saying 2 or 0 are the possible real roots. Again, I don't find it to be all that valuable information, but it's true. So he found that this is true. So you find the maximum number and then you keep kicking it down. So suppose he had found 6 sign changes. Well, then we'd find that the positive real roots could be 6, 4, 2, or 0. Again, not life-changing information, but there it is. Now, that was the positive roots. He saw that we could do the same thing. If you put negative x in to the function, tidy it up, we get down to this. Kind of like when we did with even and odds. Remember, we would put negative x in for an odd function. We're doing the same thing here, putting negative x in, tidying this all up, we get this. Now, let's look at sign changes again. So I've got one. So I went from negative to positive. Do you see what I mean as I'm going down? So I've got 2 sign changes. I change from negative to positive. I don't change again until I go positive to negative. So what we found here again is 2. And so we found the maximum possible negative real roots are 2 or 0. Again, don't forget, this always kicks down by 2. So suppose I had found 6 sign changes. Again, it could be 6, or maybe it's 4, or maybe it's 2, or maybe it's 0. It always goes down by 2. Okay, so you could create a table like this, and some of the homework systems will do this. Again, I don't really find this all that useful. Maybe if I did this more and more in the real world, there'd be thousands of options and I'd find this valuable. But here's all the things that could happen. We could have had a maximum of 2 positive real roots and 2 negative roots. Well, that would have left 0 complex. So we know we have 4 because of the fundamental theorem of algebra says that there's got to be a total of 4 roots. So maybe they were all positive and real, and maybe they were all negative and real. And then we've just gone through all the combinations. So perhaps the 2 were positive and then none of them were negative. That would leave 2 for complex. Perhaps none of them turned out to be positive and real, and maybe 2. So you see what we're doing. We're just going through all the combinations. And then maybe none of them were positive or negative and real. That would have left all of them to be complex. So we're just using his principle and turning it into a table of all the possibilities. Okay, let's try one here. So I'm going to go through and look for the positive real. And the way I'm going to do this is I'm just checking for sign changes. I've got 1, 2, 3, so I've got 4. So the possible positive real, it could be 4, there might be 2, or there might be 0. Now let's do the same thing for the negative and real. But what we have to first do is we have to change this by putting negative x in, just like we did when we were checking to see if a function was even or odd. Okay, now I'm going to tidy it up first. So if you had 4 negative x's, do you see that would go right back to where we started? If you had 3 negatives, it would become a negative. So do you remember how this works? It's like negative 1 to the 3rd power, so that'd be a negative. So I've got plus 10 x to the 3rd on that one, because it comes out negative and there was a negative in front of the 10. Now negative x squared, so negative 1 squared, that's going to just knock each other out. It's going to stay the way it was. Negative x is going to change this sign. Okay, so Yeah, they were being real easy on us here. So the negative real, if you look through here, there aren't any. We never have a sign change. So the max number of negative real is 0, and we don't have to go down because that's all we have. Okay, so the fundamental theorem of algebra says there are 4 possible roots. So if we go, we know there's no negative roots. So if we're doing, it could be, how did they do that on the, hold on, let me see how they built their little table. So positive, negative, complex. Okay, so if it turns out, we know it's always 0 negative, so it could be, if it was 4 positive, we'd have no complex. If it's 2, maybe there's 2 complex. If it turns out there's 0 positive, there's 4 complex. See, I'm just building all the possibilities here. So, and it was easy because negative was always 0. Okay, we have one more type of problem here. This is a little difficult. What we're going to do here is make a polynomial function, and then we're going to try to solve it. So this is a little different. Let me go through here. So I'm going to make, whenever I do word problems, I make a dictionary. And here I have width, length, and height. So we're doing the volume of something, of a rectangular solid. So my formula here is just going to be V equals W times H times L. Okay, so it's the volume of a rectangular solid. Now the story is going to tell us that we can build 2 of these idle no's off one of them. So what I mean is, check here, which one of them can we build off? They want the length to be 4 longer than the width. Okay, so the length is building off the width. So I'm going to call the width idle no, and the length is going to be 4 longer than the width. And now, if you've done this right, the last one is also going to be built off the width as well. The height is 1/3 the width. So I call this my dictionary so we don't forget what we're talking about here. I've translated width into math language, length into math language, height into math language. Now I'll let them take it here. So I'm going to substitute all of those into my formula. It was V equals WHL, but I'm going to now put in my idle no's. Now they left it as W. I changed it to X, but that's fine. Okay, so they create this equation for the volume, and the story told us that it's going to equal 351. Okay, so I know what the volume equals. Now they did the trick where they eliminated those fractions by multiplying everything by 3, and now we get this equation here, which is good. You don't want these fractions in here. Okay, so I've eliminated those, and now I'm going to swing this over to the other side. Now this is where we would use all of our tools, and this is brutal. Now I'm going to show you this, but this would be really hard, especially on a test, to try to figure this out. But here's a real world application. We've got our polynomial function, and we were trying to find the zeros. So look at all the possible rational zero so the rational zero theorem tells us it could be all of these choices. That could be a solution. So we're looking for a solution to that missing x. And if we can find it, we would know a possible solution for this whole word problem. But all of these are possible solutions. So that's really difficult. That's a ton of them. What I would do here is I would use the remainder theorem, have this function in my calculator, keep substituting in the different values. But so they jump right to synthetic division, which again I don't think is the best idea. But they jump there and they find they've got a remainder of -1048. So that's not a solution. Then they try again with 3, and that's not a solution. It's not a factor because, or a 0, because I've got a remainder. Now they keep jumping around and they get to +9, and they find out that that is a solution. So that has a remainder of 0. So x minus 9 factors this thing. But that also means that x equals 9 is one possible solution. Now there could be others, but if x equals 9, then I have what I need. I can then take 9, put it back. This is my dictionary here. They've written it differently. Let me go back to mine. So I've got my dictionary here. So we found out that one possible value for x is 9. Well, using that information, I can find the rest. So this is 13. This is 1/3 times 9, and I get 3. So this is one possible set of dimensions that would solve this equation. Okay, now I'm going to just talk you through another one here. You're welcome to pause the video and try this on your own if you want to. Again, these are very difficult, so I'm going to set up my dictionary here. Got my length, my width, and my height. And they're telling me the length is 1 longer than the width. So everything is again going to build off the width. So the length is 1 longer. The height must be 1 more than twice the width. You agree with that? Okay, so I'm going to use that same formula for volume, and I would have this. So this is the length, the width, the height being multiplied, and they equal 84. Now I'm not going to show you here. I went through, FOILed all this out, and I get 2x to the third plus 3x squared plus x. And now we're going to bring this over so we have this equal to 0. So now, if we could find a 0 here, if we could find a root, then we would be able to go ahead and solve this. Yeah, for a minute I was checking to see if it factors, but it doesn't. Now, once again, we're going to use this is our P over Q trick here to list all the possibilities. Now, 84 has a bunch, has a big long list. I don't even know if I should write them all out. 84 has a bunch. Q is 2, so it just has plus or minus 1, plus or minus 2. Okay, so we have a huge list here. I guess I'll start doing it. So on the P's, it's plus or minus 1, plus or minus 2. So it keeps going. There are so many of these. So you then have to do all the different arrangements of P over Q and start testing them out. Well, I've already gone ahead and done that. It turns out that 3 is going to be our solution. So if you do some, let's check it with synthetic. So let's see if 3 works, which I know it already does. Bring down 2. Okay, so this works, and I get a remainder of 0. So I know so far I've got x minus 3 times 2x squared plus 9x plus 28. That's factored. But the important part for this problem is that 3 is a solution. So I would go back to my dictionary here. If I put in 3, then the length must be 4. Width is 3, and then this is 2 times 3 plus 1, I get 6, I get 7. Now, I know that's very difficult, so you'd have to be really limited and careful about how you give a student a problem like this. On a test, it'd be almost impossible. But this is the kind of application that we're talking about, where you have an enormous amount of possibilities, and so you'd use the remainder theorem to test those out to try to narrow that down. And then, again, we learned Descartes' theorem as well here. Again, I don't find it particularly useful, but it's clever. So hopefully that makes some sense.